So this lesson is on homework 9 on Taylor series with Maple. So let's look at problem 1. Which is to compute the Taylor polynomial of degree 6 for certain functions. And the first is the function f of x equals 1 over x squared plus 1. So in Maple, if we want the Taylor polynomial of degree 6, we have to do the following. The command is Taylor. This is my function, f of x, centered around 0. We write x equals 0. And if we want the Taylor polynomial of degree 6, we have to go up to 7. And this is it. So 1 minus x squared plus x to the 4th minus x to the 6th. So the Taylor polynomial is this, and this is an estimate for the remainder term of the error. So this is approximately equal to this. So in this case, P6 is equal to that. Okay. The next problem was for the polynomial, not the polynomial, for the function, I'll call it g, call it f because that's what I did in the notes. X goes to e, here, exp of minus x squared. Yep, that's the function. And the command is exactly the same. So in this case, my Taylor polynomial of degree 6 is equal to this. And in the third case, we're looking at the tangent of x. So f is equal to x goes to tangent of x. And again, it's the same command. And this is what the Taylor polynomial of degree 6 looks like. Now, it's really very interesting to compare the function to the polynomial. So let's just graph the two of them together. So this is the function. That's the polynomial. So let's plot together f of x and this polynomial P6. Well, hard to see what's going on perhaps. So let's really just do it. This is supposed to be an approximation close to 0. Let's go from x from -1 to 1. That's really pretty interesting. So 1 over x squared is this red curve. And the blue is this polynomial. And you can see close to 0 is an extremely good fit. Very impressive. See, next we have the function e to the minus x squared. Let me call this polynomial q. And again, let's look at the two of them together. This is Q. Wow. So e to the minus x squared, that's the blue curve. And this polynomial degree 6, that's that. And again, it's a fantastically close fit. It's really very impressive. Let's go to the tangent. There's the Taylor series. Let's call this R, so please don't get confused. And again, now my function is the tangent, and R is this polynomial degree 5. Woo, look at that. Again, close to 0. In fact, it's hard to tell which is which. Let's just do an experiment. Yeah. So when I graph it like this, you can see the blue is the tangent, and the red is this polynomial. Oops. So the blue is the tangent, the red's the polynomial, and near 0, they're almost identical. That's very nice. Problem 2 is to calculate Taylor polynomials for some functions centered around x equal 1. So in the first case, x is the function 1 over x. And when we expand that around x equal 1, it looks like that. So let's just call it p. That's no reason to make it more complicated. The polynomial degree 6 is that. And let's see whether that can be simplified. Yeah, when you expand it all out, this is what you get. Let's compare the two of them. Let me just write down exactly what they are. So there's the function 1 over x, and there's this polynomial. Let's say x going from 1/2 to 3/2. Now, you truly cannot tell them apart. This is an approximation centered at 1. Let's see. Now, okay. If I go out to 5, you can see this polynomial. See, 1 over x is decaying. This polynomial is shooting up. So even out to 2. Yeah. So the red is 1 over x. The blue is this polynomial. And notice around 1 how close they are to each other. It's really quite nice. Next, we have the tangent. Let me just write it down. Taylor series for tangent of x at x equal 1 up to 7. Oops. Well, I don't know why. Oh, no, that's fine. So yeah, so it's this kind of rather complicated looking thing, but these are in powers of x minus 1. See if I make this 1.0, whether it makes a difference. Ah, perfect. So here we have this polynomial in x. Let's see if we can simplify it. No, well, it doesn't get any simpler. So this is a polynomial of degree 6, and this is the error term. That's what it is. It's not really any simpler, so let me take it up. Okay. And so this was the Taylor polynomial for 1 over x. And this was the Taylor polynomial. What happens to the log of x? Oh, let me insert that. So the Taylor polynomial for the log of x centered around 1 up to 7 is this polynomial. Let's just simplify the polynomial part. Yeah. So it's the same polynomial, it's just this is expanded and we collected the terms, and it's not really in the right order, but that's what it is. Let's take a look at the graph. Suppose I plot log of x and this polynomial from 1/2 to 2. So 1 is log x and 1 is this polynomial. And again, close to 1, you see how close they are to each other. You just can't tell them apart. It's really, these are fantastically good approximations. Okay. Problem 3 wants us to take the Taylor polynomial for the square root of x and see how many terms we need to have a good approximation to the square root of 1.5. So let's just do it like this. For n, let's say from 1 to 5 do. And what do I want to do? Well, suppose I let p be equal to, well, that's it. So compute the Taylor polynomial of what function? Square root of x centered at x equal 1 of degree n. Start at 2. So I have these polynomials. And so let me take this. This is for n equals 1. Oops. And that's what this is. 1 plus a half x minus a half is a half plus x. And let's substitute in this. X equals 3 halves. And I'll call this A1. The linear polynomial. Let me do the same thing with the quadratic polynomial. Actually, what I really need to do is to know what I'm comparing it to. Comparing it to the square root of 1.5. So square root of 1.5 is this, 1.2247. When I take the degree 1 Taylor polynomial, the degree 2 Taylor polynomial, I get these approximations. Let's look at A3. This is the cubic polynomial. Oh, not bad, getting better. This will be oops. So what I want to do is substitute x equal 1.5 into this expression. That's what we get. And when I take the 4th degree polynomial, I get that. Now, so this it's accurate to 4 significant digits. So this is 1.2247. That's the truth. This is 1.22412. So that's all you're supposed to do in this problem. Just compare these two. Oh, for n equals 2, 3, 4, and 5, I only went up to 5. So let me, there we go. Let me do this finally for the number I will call A5. So if you take this 5th degree polynomial, that's the 5th degree Taylor polynomial, and you plug it in. This is what we get. And this is, again, it's 1.2249, 1.2247. So this is better, you're getting better and better approximations. That's the whole point of the exercise. And the last is to calculate the Taylor polynomials for cosine plus sine and compare them. So this is problem 4. And for n from 2 to what? Let's see. I want the first 4 Taylor polynomials. So I'm going to go from 2 to 5, do. And what I want is the Taylor polynomial for the function cosine of x plus sine of x, centered at x equals 0. Again. So let's see. If I plot cosine of x plus sine of x, that's what it looks like. But then we plot it together with each of these 4 polynomials. So this is 1 plus x. And again, you want to look at how closely you get an approximation near 0. Okay? That's what it looks like. When you take the quadratic polynomial, that's this guy. Well, it fits a lot better near 0. That's what it looks like. There you go. Let me use the same range here. Yeah. So here's the approximation for the linear. This is the approximation for the quadratic. What about the cubic? This is the cubic. Oh, really much better. And finally, for the 4th degree polynomial, here it is. Ooh, now look at that. It's only a polynomial of degree 4, but you get this fantastically good fit between, let's say, minus pi over phi and plus pi over 4. That's what it is. Okay. So that is homework 9 on the Taylor polynomial.